Hey everyone, this is Adrian, and today I'm going to be talking to you about all things electrical. So we're going to start out by discussing the fundamental property of electrical charge, what it is and how to think about it. We'll move on to a discussion of electrostatics, which will include a discussion of electric field lines. And we'll finish off with a discussion of electricity, and we'll look at some key examples from electricity, including the DC circuit. This is the kind of circuit that you'll find in your Walkman, if anyone out there still has a Walkman, your MP3 player, your phone, etc. So let's ground our conversation about electricity, pun intended, by first discussing what exactly electrical charge is. Electrical charge, like mass, is a fundamental property of matter. It's by virtue of the fact that an object has mass that that object will be attracted to another object that has mass. The attractive force that results by virtue of two objects having mass is known as gravity. In the study of forces, gravity is unusual because it exists between two objects that are not in contact with each other. In other words, it works over a distance. Electrical charge is also responsible for a force that works over a distance, known as the electrical force. Whereas gravitational forces are always working to bring objects with mass together, electrical forces can either bring objects together or repel objects away from each other. This is because there exist two types of electrical charge: positive charge and negative charge. Electrical charge is somewhat of a nebulous concept, so it's kind of hard to represent visually. The way we usually represent it is by drawing electric field lines emanating from point charge. Electric field lines are typically drawn as going away from a positive charge and towards a negative charge. So let's draw our positive charge here and our negative charge here. And you'll see that the arrows represent away from positive and towards negative. The direction of the field lines may seem arbitrary, but there's a very good reason for why we draw them in the direction that we draw them in. The direction of electrical field lines, like many things in science, is based on an experimental convention. So imagine that we were to put a positive test charge near to a positive point charge. Imagine that the point charge is stationary, is locked in place, whereas the test charge can move. When the positive test charge is placed near to the stationary positive point charge, the test charge will experience a force that pushes it away from the stationary positive point charge. Thus, based on this experimental convention, we draw electric field lines emanating from positive point charges as moving away from the positive point. The electric field lines for similarly charged point charges will not overlap with each other. This lack of overlap is how we visually represent repulsion between two positive charges or two negative charges. Now take that positive test charge and move it near to a negative point charge. What you'll see is that that positive test charge is attracted to the negatively charged point charge. In other words, there's an attractive force between the positive test charge and the negatively charged point charge. Because the negative point charge attracts the positive test charge, we draw the electric field lines for a negative charge as being directed towards the point charge. The field lines between oppositely charged point charges will overlap to form this sort of mesh, and this is how we visually represent attraction between oppositely charged particles. The next time you're doing some MCAT review on ionic solutions, think about how electric fields are present around charged particles. So think about why two sodium ions are not attracted to each other, whereas a sodium ion that's positively charged and a chlorine ion that's negatively charged are attracted to one another. Okay, so before we go any farther, let's talk about how we quantify charge. The basic unit for charge is the Coulomb, Charge is a quantized phenomena, meaning that it comes in discrete units. The charge on a proton, 1.6 times 10 to the negative 19th coulombs, is the smallest unit of charge that we know of. This unit of charge is known as the elementary charge. So an object could have a charge that's 1 times the elementary charge, or 2 times, or 3 times, or 1,000,000 times the elementary charge, but on no charge in between multiples of the elementary charge. And a coulomb is equal to the charge of 6.24 times 10 to the 18th protons. When representing charge numerically, we represent positive charge as a positive number and negative charge as a negative number. Now let's talk about how to find the force between two charged objects. We're going to use Coulomb's law, which is F equals K, which is a constant, Q1, which is the charge on one point charge, Q2, which is the charge on the other point charge, over R squared, which is the distance in meters between the 2 point charges. I recommend using Coulomb's law to simply find the magnitude of the force between two charged particles. That means using the absolute value of the charge in your calculations. You can figure out the direction of the force by looking at the charge configuration between 2 point charges. Now that we know how to use Coulomb's law to find the force between two charged particles, let's deepen our analysis to see if we can uncover some information about a single point charge's electrical field. Imagine that I have a point charge with a positive charge of 1 coulomb. And imagine that I have a proton with a positive charge of 1.6 times 10 to the negative 19th coulombs that is 1 meter away from that point charge. What if instead of being curious about the force between the two charges, I'm curious as to the force to Coulomb ratio that exists 1 meter away from the point charge? To find the force to Coulomb ratio that exists 1 meter away from the 1 Coulomb point charge, I use the following equation. F equals Q, which is the charge of the test charge, times E. E is the force to charge ratio due to the 1 Coulomb positive point charge. To find E, which we said will be the force to Coulomb ratio due to the electrical field produced by the 1 Coulomb positive point charge, we're going to first find what F equals. And from Coulomb's law, we know that F equals K Q1, which we will take to be the charge of the point charge, 1 Coulomb, Q2, which we will take to be the charge of a proton, 1.6 times 10 to the negative 19th Coulomb, over R squared, R being the distance between the two charges, which we have said is 1 meter. We know that that entire function is equal to Q, which we are going to take to be the charge of the test charge, in this case the proton, which is equal to 1.6 times 10 to the negative 19th coulombs, times E, which is going to be our force to charge ratio due to the electrical field produced by the 1 Coulomb point charge. Dividing both sides of F equals QE by Q, the charge of the proton, we find that E is equal to 9.0 times 10 to the 9th newtons per coulomb. This means that at 1 meter distance from the 1 Coulomb positive point charge, a 1 Coulomb test charge will experience 9.0 times 10 to the 9th newtons of force.